aluminum is going to induce compression. That's why minus. The P inducing on the stainless steel is also in compression. That's why both of them are minus. Okay, so you just put minus P times by 0.3, which is the length. And the cross-sectional area is what? The cross-sectional area is 2000. The Young's modulus is 75 times 10 to the power 9. Then plus by minus P again, multiplied by the length of 0.25. And then divide by the cross-sectional area, which is 800 times 10 to the power minus 6. And then you have 190 times 10 to the power 9. That is our Young's model. Yep. Yeah, our Young's modulus. So this will be equal to minus 2 times by 10 to the power 9 minus 9p plus by minus 1.6447 times 10 to the power minus 9p. So this will be equal to minus 3.6447, right? 3.6447 times 10 to the power minus 9p. Okay, so we apply the last equation where delta T plus by delta P is equal to 0. Okay, so it is equal to 0.847 times 10 to the power minus 3 plus by and then minus 3.6477 times 10 to the power minus 9p is equal to 0. So from here, P will be equal to 0.847 times 10 to the power minus 3 divided by 3.6447 times 10 to the power minus 9. So this will come out to be, so it's equal to 0.847 power minus 3 divided by 3.6447 power minus 9 is equal to 232.392 times 10 to the power 3 Newton. Okay, so the question asked is to find the normal stress in the aluminum. So the part A, normal stress of the aluminum so this will be equal to minus P aluminum divided by the area. So this will be equal to minus 232.392 times 10 to the power 3. Why minus? Because of this, yes or no? The aluminum is induced, the PAL is inducing a compressive stress, right? Makes sense, right? The PAL is inducing a compressive stress, so it's minus, and then divide by the cross-sectional area of the aluminum. The cross-sectional area of the aluminum is 2000 times 10 to the power minus 6. So this will come out to be 232.392 power 3 divided by 2000 power minus 6 is equal to minus 116.196 times 10 to the power 6 Pascal. Okay, and then the next part of the question, okay, which is calculate the change in length of the aluminum rod. Okay, so the change in length will be equal to alpha delta T plus by L naught, okay, plus by P of aluminum, L of aluminum over E of aluminum and A of aluminum. Okay, so we know that the temperature change will do extension, and over here will induce, the load will use extension extension. What's opposite of extension? Anyone? Reduction. Right? Because it's going compression. So we know that alpha, right? We have calculated this before. Alpha. So this one over here for aluminum is plus 828, right? Times 10 to the power minus 6. We had calculated this earlier. We calculated this in over here. Okay, we calculated this over here, right? Right, the formula alpha. So this is our alpha, change in temperature, and then the length. Okay, and then we have plus PAL. So it's minus 232.392 times 10 to the power 3 multiplied by the length of aluminum divided by the Young's modulus of aluminum is 75 times 10 to the power 9, and the area is 2000 times 10 to the power minus 6. So this will be equal to 828 positive times 10 to the power minus 6 minus by, so 232.392 power 3 times 0.3 divided by 75 power 9 divided by 2000 power minus 6 is equal to 0 is equal to 464.784 times 10 to the power minus 6. Let me do it again. So 232.392 power 3 times by 0.3 divided by 75 divided by 9 power 9 divided by 2000 power minus 6 is 464. So this will be equal to 828 power minus 6 minus 464.784 power minus 6 is equal to 3. Even I'm tired already. So it's equal to 0.3632 times 10 to the power minus 3 meters, and is going towards the right hand side. So this answer seems reasonable because it's less than what? 0.5 meters. And it makes sense. The aluminum will expand more, yes or no? Because the aluminum coefficient of expansion is much higher. So for aluminum, the coefficient of expansion is what? If you look at the question, the coefficient of expansion is what? 23, right? Whereas the stainless steel is only 7.3. So aluminum is going to expand quicker than the stainless steel, okay? And if that's the case, questions, please. Thank you.
Does the rate of expansion matter depending on the area size?
The area, no. For this case, we only consider the extension. Remember what I told you, right? We are only interested in the axial expansion,
Okay.
right? Not the radial. Okay,
Okay.
it does play a part though. Okay, but the more significant is the axial expansion. Okay. Next question, please.
Yes, I have a question here. When we calculate the change in the length, should we take only the extension?
Can you repeat your question, please?
When we calculate the change in the length,
Yep.
should we consider only extension?
No, because
Because the aluminum only like
no. Let me tell
extend.
you. I'll tell you why. Because there's a heat component they have to consider. So this is due to temperature change, and this is due to mechanical loading. So you have to consider both. Okay, you cannot just consider the mechanical loading without thinking about the temperature change, because this problem is the change is due to temperature, but upon contact, right, then you have mechanical loading. Does that answer your question?
Yes.
Okay.
Thank you.
Next question, please. No further. Yep.
I have a question. So, When we calculated actual deflection, which is 0.847,
0. What?
remember we calculated actual deflection that induced the
Yep.
thermal stress?
Yep.
If you go a couple of pages back.
Yep.
So this is our delta T.
No, this is in this. What this is trying to show you is only at this distance, then you see a stress. From here to 0.5, no stress at all. This is because there's a gap. That's why we took a distance of 0.847. We did not use 1.347, did we? We have to use 0.847 because of the what? Of the gap.
Yeah, so 1 second. 0.847 is the delta T, right? The actual deflection, or no?
The actual deflection that this thing is going to see is 1.347.
But we
But
don't use it. We use the
no,
0.847.
yes, because of the gap. Because whenever there's a gap, no stress. When there's no gap, then there's a stress. And no gap onwards is at 0.847 distance change, then there's a stress. So in this region, 0.847, right? This region I've drawn, you'll see a stress build up.
Okay, so because of this gap, we're
Yes.
using
Yeah.
the 0.847. There is no like a separate letter for this value or something?
There's no what?
You know, like this, the 1.347, it's delta T, right?
Yeah, so this one, so we just call it the actual deflection, which induced
Okay.
thermal stress. Okay, there's no delta T for, yeah.
Yeah, because
Okay,
the formula says delta T
I
plus
know, but this is because
delta P.
we have to consider the gap, right?
Okay.
So that's the actual deflection. Okay.
Okay.
Anyone else? Thank you. Anyone else? One of you? Okay. Right.
Sir.
Yep.
Regarding the homework one,
Yep.
you post the checkpoint answer for number 2 and 4. I did the number 2 and 4, but I'm not sure I did it correct or not. I want to check my answer.
Answer 2 and 4.
Yeah.
Did your final answer, is your final answer correct?
Number 2 and 4 is not on the solution.
It's not on. Yeah, questions 2, 3, and 4 is not on the solutions, so you can't check.
Okay, 2, 3, and 4. Okay. I cannot post them immediately. Okay. So I need some time to work on it because I have, as I say, I can't post it immediately. Is that fine? It's the earliest I can post is probably on Sunday.
Yeah, that's good. That's good.
Okay.
Yeah, somebody
Sir?
was asking if you can open the discussion board to discuss homework and solutions.
Discussion board on Avenue to Learn.
Yeah.
Yes.
Okay. So discussion board is only y'all can attend this discussion board, right? Without me, am I right?
Yeah,
Yes.
yeah, but I don't think
Okay.
it's open though.
Okay, I will see. Look at the discussion board. I'll open. I think this is important. Thank you for asking me to do it. Okay, I did not know about the discussion board. Okay, any other questions then?